Hi, good morning. So today what we're going to do is we're going to review chapter 3, go over really quickly everything that we've done so far, and then we're going to jump into section 3.4. Okay, so let's do that right now. So we'll do it a little bit differently today, see if it helps. Usually I provide you the notes and you just print them out, but today let's go over the notes through the textbook. Maybe it might give you a different perspective. So like you can see, we have our exponents and radicals chapter here, so chapter 3. To start off with, we started with the get ready section, and here this is just reviewing using exponents, right? So this should be a review of pretty much grade 9 stuff. We're reviewing squares, most of them. Exponent laws, so when you multiply two numbers of the same base, divide two numbers of the same base, etc. So 3.1, we talked about square roots and cube roots, and just some terminology that you should be familiar with. Perfect squares are a number that has a factor multiplied by itself, gives you that number. So for example, a perfect square would be 4, because 2 times 2 is 4. Another perfect square would be 9, because 3 times 3 is 9. Another perfect square, 25, 5 times 5 is 25, etc. Square roots would be, the factor that multiplies itself to get to that perfect square, right? So the square root of 25 would be 5. 5 times 5 is 25, right? So you can read about that there as well. Perfect cubes and cube roots, same sort of things, but now we're doing the same factor times 3. So a perfect cube would be 27 because the factor 3 multiplied by itself 3 times, so 3 times 3 times 3 is 27, right? Another perfect cube could be 125 because the factor 5 times itself 3 times, 5 times 5 is 5, gives you 125, right? So we just talked about that. And then in this section, we also talked about prime factorization. So if you don't have a calculator and you want to find if a number is a perfect square or a perfect cube, what do you do? So you break it down. Right here, you can see the top right. By just thinking about two numbers that multiply together that gives you 729, and you keep breaking it down. So 3 is a prime number, so you can't really break it down anymore. So we just carry the 3 down. But the 243, 3 times 81 gives you 243. 3, you can't break it down again. Then the new 3, the 81, you can break down to 3 times 27. The 27, you can break down to 3 times 9. And you carry it down. To the very end, you're left with um, 6 threes. And then in this case, we're looking for the perfect square. So you pair them up. So 3, 3, 3, 3, 3, 3, and you multiply them. 9, 9, 9. So this is confusing. You could read the notes here. I also went over it, obviously the notes I posted on 3.1. Okay. So prime factorization, you could do it to find perfect squares. You can find it to find perfect cubes, like on this section here. Just on perfect cubes, you're pairing them up. Oh, not pairing, but you're grouping them up into groups of 3 this time instead of pairs, and then you take 1, 2 out, and you multiply. So here there's take 1, 2, another 2 here, another 2 here. So 2 times 2 times 2 gives you 8. Okay. Then you had the question on that section. And then 3.2 was integral exponents, which are basically exponents to the whole number. So we're not dealing with fractional exponents. And the main thing you need to review here is the exponent laws. You can see in the top left here. So you got your product rule. When you're multiplying a number with the same base, you just add the exponents. Quotient rules, when you're dividing numbers of the same base and their exponents, you just subtract them. So m minus n over here. Maybe it might be better if I zoom in. Okay, there we go. Maybe this might be a little bit better. So yeah, so we could look at the power rule. The power rule, when you have exponent to an exponent, you multiply it, so m times n. Product rule, so if you got an exponent and you have the two different bases inside, you can just basically put the exponent onto each of them, so a to the power of m and b to the power of m. Same thing, so power of a quotient, you can, the n on the outside goes to the top and the bottom. And finally, an exponent to a base to the exponent of 0 would just be 1. Okay. So review that, just make sure you kind of remember it by heart. Obviously you can use a chart, but that's something you should just remember. And then we also got, I think we talked about the base 10 a bit. Let's go to the next page here. And that's pretty much it. This whole section is talking about using the exponent laws. So each example here, just going through, here's a power rule. applying powers of integral exponents. So here, oh, this is something some people had a lot of questions on as well. I'll provide an example. Um, yeah, I'll provide an example in the notes. I'll go over one of the questions people were having difficulty on. But for now, when you have a number like this is actually one number where it says 9 times 10 to the power of 6. Right here, what the answer is. Some people are treating these two separate kind of numbers here. So 10 to the power of 6 just means 9 times 10 to the power of 6, which gives you 6 zeros, right? So it's writing this number, 9 million, in a shorter way, okay? That's all it is. So don't treat these as two different sections. I think that kind of confused people on some of the written questions. So I'll just go over one of the written questions and post it, and you can take a look. Okay. Quickly going through this section a little bit more. That was about it for 3.2. Section 3.3, rational exponents. So this is going to be, it could be exponents with whole numbers, but it could also be exponents, fractional exponents as well. As long as you can put it as a fraction, right? So we're not looking at radicals here, but so here, for example, you got number 1, 9 times 1 over 2 times 9 times 1 over 2. So what do you do here? You're basically just going to add these fractions like just like normal. And when you're adding fractions, just make sure the denominator is the same. So 2 and 2, so it's the same. So you can just add the numerators together. 1 plus 1 is 2. So 2 over 2 gives you 1. And 9 to the power of 1 is just 9, right? So you should know how, from grade 9, how to add and subtract fractions. Just make sure the denominator is the same. So if it's not the same, then you have to make it the same by multiplying the top and the bottom. So okay, so let's go through this again. So same sort of idea, just applying exponent rules to fractional exponents basically. Here, part A, let's see what they're doing here. Oh, they're solving this multiply or divide powers of the same base. Again, just add the exponents. So 1 over 3 here, 5 over 3 here. So we add it, so it's going to be 6 over 3. 6 over 3 simplified is going to be 2, right? So 5 to the power of 2. That's how they got it, right? So same thing here. B, like for example here, you can just add the exponents here. So maybe I'll zoom in. So I'm not sure if it's easy to see here. So over here in B, you have to, there's an invisible 1 here. So 5 over 1. They wrote it right here. They didn't really write the 1, but it's 5 over 1. So to get the same exponent on this side, you have to multiply it by the denominator. So it's 2 here, so you times the top and bottom. 5 over 1 by 2. So 5 times 2 is 10. And 1 times 2 is 2. So 10 over 2 here. And then now you can just add them. So 10 minus 1 will give you 9. So 9 over 2. Right. So we can't go over all these examples. They're pretty much the same as the ones I went over the notes. So take a look through here if you want some extra notes, and let me know if you have questions in this section. Okay, and today we're going to move on to extension, introduction to radicals. And I'll talk about that in the next video. So I'll just post this up as a quick review, some extra notes in the chapter, and the next video will be 3.4. Right?